In future lessons in this course, we will find that we have the need to evaluate limits that result in indeterminate forms that cannot be navigated around by the usual methods. In Calculus 1, we saw limits that resulted in 0 over 0, one indeterminate form, and we were usually able to get around that by some careful algebraic manipulation of the expression in question. If it was a rational function, perhaps we were able to factor the numerator and denominator and create another form that was equivalent everywhere except perhaps at the target value, and that was good enough to get around the indeterminate form. However, there are some functions where the algebra to do so is not nearly so obvious, or perhaps even out of our grasp entirely. So we are going to need a new rule for how to deal with that. So let's first talk about the indeterminate forms and why it is they are indeterminate. The two indeterminate forms that we would have encountered through Calculus 1 were a limit that resulted in 0 over 0 and a limit that resulted in either positive or negative infinity in the numerator over positive or negative infinity in the denominator. Now, at the time, seeing infinity over infinity, a common thought might be, well, if you've got the same thing top and bottom, then it should be equal to 1. The problem is that infinity isn't something you can actually reach. So, interestingly enough, the numerator and the denominator may not actually be the same value. And that's the important thing to realize here, is that we're not talking about a fraction where we actually have 0 or infinity in the numerator and denominator. We're talking about an expression that is approaching 0 or approaching positive or negative infinity in the top and bottom. And that's why it's not so simple as saying, well, infinity over infinity must be equal to 1. We know from having seen examples in Calculus 1 that that is not the case, that there are very often times where a rational function that resulted in infinity over infinity may have come out to a value of 0, or may have come out to a non-zero value, or may not have even existed at all. So infinity over infinity is not so simple as that. And that is because we have to consider how the numerator is approaching infinity or approaching 0. And the reason is that when the numerator of a fraction approaches 0, that means the value of the fraction is getting smaller and smaller and smaller. But when the denominator is approaching 0, that makes the value of the fraction bigger and bigger and bigger. So you have the numerator and denominator fighting for control, where one of them is trying to make the fraction very, very small, while the other is trying to make it very, very big. So how we resolve that is we have to look at how quickly is the numerator approaching 0, and how quickly is the denominator approaching 0. Because whichever one is approaching more quickly is going to win in terms of control. Or perhaps they are approaching at a comparable rate, which means that we might end up with a non-zero, non-infinite value for the limit. The same is true with the infinity over infinity indeterminate form. The numerator getting larger is trying to make the fraction larger, whereas the denominator getting larger is trying to make the fraction smaller. So we have the inverse of what we saw with the 0 over 0 form. In this case, it's the numerator trying to make it big and the denominator trying to make it small. So again, it becomes a matter of which one is getting there faster, being the one that's going to control what's going on. Or are they approaching infinity at a comparable rate, in which case we could result in a non-zero finite value for the limit. As it turns out, there are other indeterminate forms that we would not have encountered in Calculus 1. to list them here, we have an indeterminate form 0 times infinity, which is actually very closely related to the previous two, because the previous two are based on division, whereas this is based on multiplication. And we have the same situation where the multiplication by 0, or by something that again is approaching 0, is attempting to make this product very small, whereas the thing that is approaching infinity is attempting to make the product very large. So again, we have that tug of war, and we need to look at how quickly each one is approaching what it's approaching. There are a couple of exponential indeterminate forms. One of them is 1 to the infinity power. Now, quick logic would suggest that if an exponent is approaching infinity, that we are multiplying the base by itself many, many, many times, but that doesn't necessarily make something particularly big or particularly small, because it depends on the base. Any base larger than 1 represents a growth function, and as the exponent approaches infinity, that function should approach infinity. So in the case of a base that is larger than 1, this should approach infinity. On the other hand, a decay function, when the base is smaller than 1, but still positive, a decay function approaches 0 as the exponent approaches infinity. So we now have, again, that tug of war almost, and it's going to be based on, in this case, not so much the exponent, but it's going to be based on the base, and whether the base approaches 1 from above or whether it approaches 1 from below. Another exponential indeterminate form is 0 to the 0 power. This is indeterminate because a non-zero positive base to the 0 power should be equal to 1 based on the progression of positive integer exponents as we're decreasing. As we decrease the exponent, we are essentially dividing by the base. The problem here being we cannot divide by 0. So now we have to consider that the base is approaching 0, but furthermore, by the rules of exponential functions, it has to be approaching 0 from above. So we are looking at a positive base that is getting smaller and smaller and smaller. At the same time, we are looking at an exponent that is also getting smaller and smaller and smaller. Now, with a large value, with a base such as 2 or 3 or 5, as the exponent approaches 0, we should be shrinking and shrinking and shrinking until we were approaching 1. However, in this case, where the base is also approaching 0, we run the interesting question of, does this actually go towards infinity? Because the smaller the base, when we multiply by itself, that should actually make everything very, very small. But we're also multiplying it by itself fewer and fewer times. Now, the analogy of multiplying by itself ceases to be useful as we get into fractional powers, especially as they get smaller and smaller towards 0. So what we're looking at basically is we're taking smaller and smaller roots of a smaller and smaller number. So it's not very clear what that's going to be approaching. Hence, indeterminate forms. One more indeterminate form we will come across is infinity minus infinity, which again, at first, might seem intuitive to say, well, anything minus itself is 0, until we consider again that we're not looking at actual infinities, we're looking at something that is getting larger and larger and larger, minus something else that's getting larger and larger and larger. Meaning that we now need to talk about which one is getting larger faster. Or are they getting larger at some kind of comparable rate? Each of these, we have to look at the rate at which they are approaching their respective values. Each of these things has two components. So we need to be able to break down whatever expression we're looking at into the two components. So to establish this rule, L'Hopital's rule, we're going to start with the idea that we have two functions and in order to talk about their rates, they must be differentiable. They will be differentiable on some open interval, which we will call I, containing a target value. That target value is where, if we took the limit as x approaches it, we would result in an indeterminate form. Now, in some cases here, specifically the 0 over 0 and the infinity over infinity, actually more specifically the 0 over 0 here, we need to avoid having a 0 in the denominator. So we're going to establish this as a rational expression where we look at the numerator and denominator as these two functions f and g. Without loss of generality, we will assume f to be the numerator function and g to be the denominator function. And as such, we need g's derivative to not come out to be 0. Except perhaps at the target value. This should be reminiscent of what we've seen as the definition of a limit in Calculus 1 that says that the function doesn't have to exist at the target value, but it has to exist around it. And this is because the limit looks at the values of the function as we approach the target value, not what's happening at the target value. So at the target value, if g prime happens to be 0, that's okay. We will deal with that if it occurs. But it doesn't really matter whether it does for the most part because we are concerned in doing a limit at what's happening as we approach x equals a. So if the limit as x approaches a of f of x over g of x results in an indeterminate form, 0 over 0, or infinity over infinity, where we can have positives or negatives in the top or bottom. If that is the case, then the limit of the two functions is actually equal to the limit as x approaches a of their derivatives in ratio to each other. Now, I'm not going to go into the proof of this because there are 3 different cases to consider. One of them is to consider what happens when when we result in 0 over 0. Separately, we would need to look at what happens when x approaches a finite value a, and we result in the positive or negative infinity in the top and bottom. And the third case actually deals with what happens if x is approaching infinity, which is where in previous things we have seen the infinity over infinity indeterminate form. So there is a secondary part of this. If the limit as x approaches positive or negative infinity of f of x over g of x would result in positive or negative infinity. In the numerator and denominator. Then very much the same, the limit as x approaches infinity of f of x in ratio to g of x is equal to the limit as x approaches infinity of the derivative of f in ratio to the derivative of g. Basically, that if the limit of a fraction results in either of these indeterminate forms, then we can take the limits of their derivatives instead. Now, those three separate cases, the proofs get a little bit in depth, a little bit complicated, and they are best proven with the proper definition of a limit, which is more complicated than we would have seen in Calculus 1. I would reserve that further proof for students who are eventually going to go into a course called Real Analysis, where they will be able to have the tools necessary to prove this to the extent that is necessary. So I'm going to omit the proof. However, we will do examples to see how it works. We will start with the indeterminate forms that we are more familiar with. Suppose we have the limit as x approaches 3 of x squared minus 5x plus 6 over x squared minus 9. By previous methods in Calculus 1, we could factor the numerator and factor the denominator, and if there are any common factors, we could simplify them out, thus producing a form of this function that is equivalent everywhere except for the value that would make the factor removed equal to 0. In fact, let's review that method. We would start by evaluating the limit through direct substitution to show that such algebraic manipulation is necessary. The numerator is a continuous function, the denominator is a continuous function, so each one can separately be evaluated by direct substitution. However, in evaluating the numerator, we would find that it results in 0, while evaluating the denominator also results in 0. Now this, of course, did not mean that the limit did not exist. It meant that we needed to find a new form of the expression that was equivalent everywhere except perhaps at x equals 3. And we did that by realizing, as I mentioned before, that we can factor the numerator and we can factor the denominator. And if they share a common factor, we can simplify it out, thus producing a new limit, a new expression that is equivalent to the original expression everywhere except at x equals 3. However, since a limit is only concerned with the values as we approach x equals 3, these two, the original expression and this new expression, are equivalent everywhere that the limit is actually going to operate. And that allows us to get by with using direct substitution. So even though the initial form of this was 0 over 0, we can see through this algebraic manipulation that we come out with 1 over 6. Now we're going to apply L'Hopital's rule to verify that it does in fact give us the correct answer, 1 over 6. So we're going to take the same limit we already showed that this results in the indeterminate form 0 over 0, but that is an important step in using L'Hopital's rule. That is a necessary requirement. L'Hopital's rule only applies when direct substitution results in the indeterminate forms. Thus, by L'Hopital's rule, the limit as x approaches 3 of x squared minus 5x plus 6 over x squared minus 9 is going to be equal to the limit as x approaches 3 of the derivative of x squared minus 5x plus 6 over the derivative of x squared minus 9. Please note that this is not the quotient rule. We are doing the derivative of the numerator and the denominator separately. The derivative of the numerator, then, is 2x minus 5, where the derivative of the denominator is 2x. At this point, we can attempt direct substitution again. In the numerator, then, 2 times 3 is 6, minus 5 is 1, and the denominator, 2 times 3 is 6. And thus we have produced the value of the limit as shown by a more familiar method just a few moments ago. This is an example to show that L'Hopital's rule does indeed produce the correct results. Now you might say, well, why would I need a new method if the old method worked just fine? Well, because sometimes there are functions that do not have an equivalent algebraic form that is achieved quite so easily as by factoring. For example, suppose we have the limit as x approaches 0 of e to the 2x minus 1 over x. Now, the top is technically a difference of squares and could be factored, but neither one of those factors is going to be x. So we're not going to get something that cancels out the factor in the denominator that's making the denominator 0. Now, the first thing we have to do before running off to use L'Hopital's rule is we have to show that direct substitution results in an indeterminate form. So if I do a direct substitution of 0 for x, clearly I'm going to have a 0 in the denominator. In the numerator, I'm going to have e to the 0 minus 1, where e to the 0 is 1, and therefore 1 minus 1 is 0. So I do indeed produce the indeterminate form by direct substitution. This now allows me to use L'Hopital's rule. Which says that the limit as x approaches 0 of e to the 2x minus 1 over x is equal to the limit as x approaches 0 of the derivative of e to the 2x minus 1 over the derivative of x, which again is not the quotient rule. L'Hopital's rule and the quotient rule are easily mistaken with each other. Please be careful of that. The derivative of the numerator will be 2e to the 2x, and the derivative of the denominator will simply be 1. At this point, we have broken the indeterminate form because the denominator being constant, a non-zero constant, means that direct substitution will not affect it. The denominator will always be 1. Therefore, we have broken the indeterminate form. Direct substitution now would give us 2e to the 2 times 0 over 1, which would simplify to 2 over 1, or simply 2. This is a limit that we would have had no other alternative to this point but to approach with a numerical method. We would have to establish a trend of x values that was approaching 0 from the left and evaluate the function at each of those x values, and then do the same thing with this trend of x values that was approaching 0 from the right, and again evaluate the function at each of those x values, which is a solid method. The numerical method is very solid. It always will work, but it is also time-consuming. Many functions that we don't have the algebra to work with are similarly going to produce very difficult decimal numbers. So the numerical approach is going to primarily be used in functions that, while the algebra doesn't work, they are also going to produce more complicated numerical values. So it is cumbersome. It is time-consuming. But it will always get you there. On the other hand, we now have this rule, L'Hopital's rule, which will allow us to get around the need for the numerical method, which is certainly preferable. We're going to go through examples that result in each of the indeterminate forms. The next one up will result in the indeterminate form infinity over infinity, which typically, not always, but typically happens when x approaches infinity. This time, our expression is the natural log of x over x. Certainly, there is no algebra that's going to help us here. Again, we have to show that direct substitution results in the indeterminate form. We need to begin there. That is always necessary before using L'Hopital's rule. Well, direct substitution here is a little bit weird because we can't actually evaluate these things at infinity, but we can talk about what happens to these functions as x approaches infinity. We know that the natural log function does increase on its entire domain. And furthermore, it does not have an upper bound. It does not have a horizontal asymptote that it approaches. It does grow forever. It might grow very slowly, but it does grow forever. Thus, it will eventually reach positive infinity if we go far enough. And I hope fairly obviously, the denominator simply being x, if x is approaching infinity, then the denominator is also approaching infinity. So we do indeed produce the indeterminate form infinity over infinity. That means that we can use L'Hopital's rule. The limit as x approaches infinity of the natural log of x over x is therefore equal to the limit as x approaches infinity of the derivative of the natural log of x over the derivative of x. The derivative of the natural logarithm is, of course, 1 over x, where the derivative of the denominator, x, is just 1. At this point, we can simplify that expression to simply write it as the limit as x approaches infinity of 1 over x, which, again, has broken the indeterminate form because the numerator will no longer approach infinity. Direct substitution now will give us 1 over something that is approaching infinity. Now again, the reason that infinity over infinity is an indeterminate form is because the numerator growing is trying to make the fraction larger, while the denominator growing is trying to make the fraction smaller. In this case, since the numerator is fixed at the constant value 1, we only have the effect of the denominator growing, which in turn makes the fraction smaller. And thus, this limit is equal to 0. Before moving on to our next indeterminate form, it is important to show that there are situations where L'Hopital's rule does not immediately produce a limit that can be evaluated. For example, suppose we have the limit as x approaches negative infinity, just to mix it up a bit, of x squared over e to the negative x. Again, we start with direct substitution to show that L'Hopital's rule will apply. if we have something that's approaching negative infinity, and then being squared, that means we will have the numerator approaching actually positive infinity. A negative number multiplied by itself will result in a positive number, and a very large negative number multiplied by itself will result in a very large positive number. In the denominator, we then have e to the negative something that is approaching negative infinity, which would then become e approaching something that is, e raised to something that is approaching positive infinity. An exponential function base e is, of course, a growth function, which means while the numerator is approaching infinity, the denominator is also approaching infinity. Thus, we have achieved the indeterminate form, which means we do not have a value for the limit, but in turn tells us that L'Hopital's rule can be used. So the limit, the original limit, is equal to the limit as x approaches negative infinity of the derivative of the numerator x squared over the derivative of the denominator e to the negative x. The derivative of the numerator then is 2x, while the derivative of the denominator is negative e to the negative x. Direct substitution here in the numerator, we have 2 times something that is an incredibly large negative number, resulting in something that is an incredibly large negative number. Now, in and of itself, that's not bad that the numerator still is approaching a positive or negative infinity, because as long as the denominator does not also continue to approach a positive or negative infinity, then we have broken the indeterminate form. However, as we saw earlier, when e to the negative x, as x approaches negative infinity, that will eventually approach infinity, but this time we have a negative sign in front of it. So this time, the denominator is going to approach negative infinity. And thus, we still have an indeterminate form. However, imagine that this was the original function. If I had started out giving you this limit is the original function, then what we just did would have shown that we could use L'Hopital's rule on this original function. So why not use it again? We saw a similar situation in integration by parts, where applying the integration by parts formula resulted in an integral that still required integration by parts. Well, we can do that with L'Hopital's rule. If the result of L'Hopital's rule still results in an indeterminate form, then we can now use the second derivative. So at this point, we now work with the first derivative of the numerator and the first derivative of the denominator, and we say that the limit of that is equal to the limit of the derivative of the new numerator over the derivative of the new denominator. And in this way, what we see is that the numerator now drops to a constant. And that is enough to break the indeterminate form. The denominator will flip signs again and return to e to the negative x. And as we saw earlier, as x approaches negative infinity, e to the negative x will approach in positive infinity. And this will result in 0. So both functions are approaching infinity initially. But as it turns out, and it took 2 steps to get there, as it turns out, the denominator is approaching infinity much more quickly than the numerator is. Let's look at some of the other indeterminate forms. Another limit as x approaches infinity. This time our function is e to the negative x times the square root of x. Once again, we have to start with direct substitution. We always have to start there to show the indeterminate form. Without the indeterminate form, L'Hopital's rule does not work. So we have e to the negative something that is approaching infinity times the square root of something that is approaching infinity. As we saw in the previous example, when e is raised to a negative large power, it approaches 0. However, the larger the value we take the square root of, the larger its square root will be. So if the value we are taking the square root of becomes infinitely large, its square root will eventually become infinitely large. The way to get around an indeterminate form that results in 0 times infinity is usually quite simple. We simply have to reciprocate one of the 2 factors. In this case, since the e to the negative x already has a negative exponent, that is the, I hope, obvious choice to reciprocate. We can move it to the denominator where it becomes e to the positive x. This changes the indeterminate form. Consequently, to infinity over infinity, which is the form that we need in order to use L'Hopital's rule. So when we do achieve an indeterminate form that is not 0 over 0 or infinity over infinity, we will need to manipulate the expression to be in the form that it would result in 0 over 0 or infinity over infinity. Now we are ready to use L'Hopital's rule. So the original limit was e to the negative x times the square root of x, which we are now saying is equal to the limit as x approaches infinity of the square root of x over e to the x, which L'Hopital's rule in turn tells us is equal to the limit as x approaches infinity of the derivative of the square root of x over the derivative of e to the x. The derivative of the square root of x is 1 over 2 times the square root of x, while the derivative of e to the x is e to the x. To clean this up a bit, we can simplify it to be written as 1 over 2 times the square root of x times e to the x. And in this way, we have, again, broken the indeterminate form because the numerator will now always remain a constant 1. So evaluating the limit is a matter of simply showing what does the denominator do. Direct substitution here will give us 1 over 2 times the square root of something approaching infinity times e to the power of something that is approaching infinity, both of which we know approach infinity themselves. So our denominator is growing incredibly large while the numerator remains a 1. And thus, this expression will approach 0. Now, you may have noticed we're getting 0 an awful lot. We also get infinity relatively often, depending on the nature of the functions. The idea is that they are not approaching their respective values, either 0 or infinity, at a comparable rate. One of them is far exceeding the other. And whether it results in 0 or infinity is simply a matter of which one of them is in the numerator and which one of them is in the denominator. If this had been the other way, if it had been e to the x in the numerator with the square root of x in the denominator, it would have resulted in exactly the reciprocal expression, and thus we would have had 2 square root of x e to the x in the numerator with 1 in the denominator. And thus the limit would have approached positive infinity and not existed, which would then in turn show that one of these functions is approaching infinity faster than the other. Specifically, e to the x is approaching infinity faster than the square root of x. If you consider the graphs of the functions, that should also be relatively obvious. E to the x goes so steep as to appear to be vertical, while the square root of x is so flat as to appear almost horizontal. So e to the x is clearly growing much faster than the square root of x. We have a few other indeterminate forms to look at, including the exponential ones. Suppose here we have the limit as x approaches infinity of 1 plus 1 over x raised to the x. Now again, we start with direct substitution as always. We have to show an indeterminate form. One plus 1 over something that is approaching infinity raised to a power that is approaching infinity. The fraction 1 over something approaching infinity is going to approach 0. So the base of this is going to be approaching 1. While the numerator approaches infinity. I'm sorry, the exponent approaches infinity. So we definitely result in the indeterminate form 1 to the infinity power. Unfortunately, this is not as quick and easy as the previous example where we simply had to reciprocate one of the functions. In this case, in order to get this into the 0 over 0 or infinity over infinity form, we're going to need to be a little sneakier. What we can do here is write y equals the limit as x approaches infinity of 1 plus 1 over x raised to the x. And what we can do is take the natural logarithm of each side. That is one approach that is often used. It's not my preferred approach, but it certainly is one that is often used. My preferred approach is to be a little bit more creative and use the inverse relationship of exponentiation and logarithms, specifically with base e. We know that base e exponentials are the best exponentials to use in calculus. We can rewrite the limit by introducing a new expression, a new operation, as long as we immediately thereafter introduce the inverse operation. So I'm going to introduce a natural logarithm of our limit, but in order to balance it out, I need to do an e raised to the natural logarithm of the limit. Now, we would get the same effect in solving this down below, because eventually we're going to have to deal with that natural log of y on the right and return it to its original y. So eventually we would have to deal with it. In fact, the way we could show that right now is to say e to the natural log of y is equal to e to the natural log of our limit, which is exactly what I did in the other form. The other form just gets us there a little bit more directly. So my preference is to simply go directly to this by introducing the natural logarithm of the limit and then raising e to that power. Whichever way you do it, though, eventually you arrive in the same place. So what we have here is that the limit as x approaches infinity of 1 plus 1 over x to the x is equal to e to the natural logarithm of the limit as x approaches infinity of 1 plus 1 over x to the x. There is a property of limits that deals with a composition of functions that says if we take the limit of the inside function first and then compose with the outer function, it is the same thing as composing the functions first and then taking the limit. What that essentially means is that we can interchange the order of the limit and the natural logarithm. What this allows us to do is with the natural logarithm directly next to our exponential expression, we can use a property of logarithms, the power property of logarithms, to take the exponent x and move it down in front as a multiple. This breaks the exponential form 1 over infinity, but it does not produce the fraction form of either 0 over 0 or infinity over infinity, but it does produce a multiplicative form. Continuing with this, we are now able to evaluate the limit by direct substitution. this will be the factor of x approaching infinity times the natural logarithm of 1 plus 1 over the denominator, which approaches infinity, which we already said approaches 0. 1 over the 1 over x term approaches 0, so that we are essentially left with the natural logarithm of 1, which is 0. So the x factor approaches infinity, while the natural logarithm factor approaches 0. And that is the indeterminate form we saw in the previous example. The way that we get around that is to reciprocate one of these factors. We either have to reciprocate the x, or we have to reciprocate the natural logarithm of 1 plus 1 over x. Now, even just by the sound of it, I think it would be much simpler to reciprocate the x. So we're now going to have a fraction where the natural logarithm factor stayed in the numerator, and the x goes into the denominator where it's going to become x to the negative 1. This will now cause the direct substitution to result not in infinity times 0, but instead the numerator, still natural log of 1 plus 1 over x, will still approach 0, while the denominator now, as x approaches infinity, x to the negative 1 will actually approach 0 as well. So now we have rewritten this limit into a form that does allow us to use L'Hopital's rule. So we take our new fractional form of the limit, and apply L'Hopital's rule to it to say that the limit as x approaches infinity of the natural logarithm of 1 plus 1 over x to the negative first is equal to the derivative of the natural logarithm of 1 plus 1 over x, which I'm going to choose to rewrite as x to the negative first for the purposes of differentiation. And in the denominator, the derivative of x to the negative first. In the numerator, then, the derivative of the natural logarithm is 1 over the expression in the inside of the natural logarithm times the derivative of the inside function. In the denominator, the derivative of x to the negative first is negative 1 x to the negative 2. So that we have a clean simplification which leaves us with a much simpler limit as x approaches infinity of 1 over 1 plus 1 over x. At this point, I will return the x to the negative first to its original form of 1 over x. Because our next step is to use direct substitution to evaluate this limit. Because we have now broken the indeterminate form, the numerator is now a constant 1. So what will happen with this is going to be dependent on what happens in the denominator. But as we've already seen from talking about the natural logarithm, or rather the expression inside of it, when the x approaches infinity, that expression approaches 1. So as x approaches infinity, the denominator of this expression will also approach 1. Now, we are not done with the problem. Remember that this started out as e to the limit as x approaches infinity of the natural logarithm of 1 plus 1 over x to the x. And through a series of algebraic steps, we turned this into e to the limit as x approaches infinity of 1 over 1 plus 1 over x, which means that overall, this limit is going to be equal to e to the first. Thus, our original function, our original limit, x is approaching infinity of 1 plus 1 over x to the x, is equal to e. This is actually a limit that you will see fairly often. It is a very well-known definition of the value of e. It's something you may actually have seen before in talking about compound interest and how if the number of compoundings approaches infinity, which should sound familiar now, then it results in a new form, the continuously compounded interest formula, which was base e. So you may have seen something like this before, just without the phrase limit in front of it. But this is a rather important definition that comes up many times in calculus. It is one of several ways that e is defined.